This additional part of the fundamental theorem of calculus has some fantastic powers because we now have this function h, which is given to be the integral from -1 to x of f of t dt. So because of the second part of the fundamental theorem of calculus, we can also state that h prime of x is equal to f of x. Okay, we're just replacing the t with the x. So this is a true statement, which means when we're told that we're given the graph of f down here, well, f is h prime. That means we're actually given the graph of h prime as well. On the AP exam, the writers love to tell the students that they're given the graph of f, and then they ask all these questions about h. And as long as you're aware of this part of the fundamental theorem of calculus, then this is just review material. We're given a derivative graph, and we're asked questions about the function. So we're just going back to all the connections between a function and a derivative, which we learned earlier in the year. Part A says find the values of x for which h has a critical number. Critical numbers occur when the derivative is equal to 0. Well, here's the graph of f, but it's also the graph of h prime. When does this graph equal 0? Exactly here and there. All right, so we're going to say at x equals, well, this is -1, and then this is when x is equal to 1. Just by writing that down, we're earning some points on the exam. Now we have to label each of these as either a relative max, a relative min, or neither. Well, let's look at this first point. The derivative changed signs, didn't it? It was positive, and then it became negative. It went from above the x-axis to below the x-axis. So because the derivative changed from positive to negative, that means that we have a relative max. Okay. We have to give a reason why, so we're just basically going to say because f, which is equal to h prime, changes from positive to negative. How about at x equals 1? Well, prior to this spot where the derivative is equal to 0, our derivative is negative. And afterwards, it's negative as well. The derivative did not change sign. So, neither. Right? Because f, which is equal to h prime, does not change sign. So it's a critical number, but it's not a relative extreme. Part B asks for us to state the interval in which h is increasing. All right, well, a function is increasing when its derivative is positive. We see here the derivative graph, and the derivative graph is positive when it's above the x-axis, which is in this zone right here. So we are looking at -4, that's when we start, until we hit -1. So from -4 to -1, h is increasing. I guess we should write that down. H is increasing on the interval from -4 to -1 because h prime, which equals f, is positive. Part C says state the values at which h has a point of inflection and give a reason why. All right, so the reason why is when the derivative changes from positive to, from increasing to decreasing. I was about to say positive slopes to negative slopes, which you could also say. From increasing to decreasing, or vice versa, decreasing to increasing. So we want to look for when h prime has, in essence, a relative max or a relative min. So we go back to our picture. All right, we're increasing a derivative, and then the derivative is decreasing, relative max. And now we're decreasing, and then we're increasing. All right, so right at that spot, that's where the derivative has a min. And then the derivative has another max right there. So there are 3 values. And those 3 values, as we can see from the graph, are x equals -2, 0, and 1. Finally, we need to state the intervals in which h is concave down. All right, h is concave down when h prime, which equals f, is decreasing. When the derivative of a function is decreasing, that function is concave down. So when is our graph decreasing? Well, it starts at -2 and it's decreasing throughout this whole time all the way to 0. And then it decreases again from 1 to 3. So we will say h is concave down from -2 to 0, and also from 1 to 3, because h prime, which is f, is decreasing.